All right, guys. I would like to start talking about the T distribution again and using T tests for hypothesis testing. This will be the last day we kind of focus on this aspect of hypothesis testing. Tomorrow I'd like to get into proportions. And then after we talk about proportions, we'll get into differences between means. So that's kind of the layout. Hopefully by the end of the week we get those two things accomplished. Remember, a T test differs from a Z test. A T test is necessary when the sample is small and sigma, or the population standard deviation, is unknown. Okay. If the population standard deviation is unknown, then the best replacement for it is S, which is the sample standard deviation. Okay. Still going to use p-values, still going to use critical values, and you still use them in the exact same manner that we did with the Z distribution. Okay. And then when we want to find our test statistic, the thing that we're going to compare, whether using p-values or critical values, you still have to find T equals X bar minus mu, your sample mean minus the population mean, divided by S over root N. Okay, and S, if you remember back to the Z distribution, the only thing that's different in this formula is that S now replaces sigma. Okay, so hopefully we can make that transition into this and really have hopefully little to no issues, because it is identical to working with the Z distribution, except for that replacement. We also have to remember that the T distribution is a family of curves, and we have degrees of freedom in n-1, and the only thing that's going to really impact is when we use our commands on Excel, or if you use your TIA3 to gain areas for p-values, or to get critical values, you're going to type in degrees of freedom. Okay. Is that okay with everybody? The one thing that I'm seeing, and we'll talk about this because it happened to a lot of us on the quiz on Friday, is that we are getting critical values and p-values confused. Okay, so I want to run through just a quick scenario of what we're doing with those things. Okay, which one's which, and how we make the decisions based off those. So let me just grab that. All right, so if using critical values, the critical regions are defined by alpha. Okay? So let's say in our case, let's just say alpha is equal to 0.05. Okay? And let's do a left tail test. Okay? What we want to do with that situation is we will find in Excel, okay, we'll set equals, okay, T, I and V. All right, now it's going to ask me for the probability. That probability that they're asking for here is the left cumulative area underneath the curve. Okay, so because we're at a left tail, that's all we're interested in. So I'm just typing 0.05 as my alpha, and let's just say for whatever reason, I think we had a sample size in one of our questions last week of 15. So let's just use 14 for our degrees of freedom. Okay, so we have 15 samples, or 15 objects in our sample, and it gives back that score right there, negative 1.76. Negative 1.76. So we find that on here. So that t-score, that critical value that is attached to alpha is negative 1.76. Okay? And because it's a left-tailed area, we are going to be interested in that region there being your rejection region. Okay? So if you find a t-score from your data, so that formula in number 4 up there, the bullet number 4 up there, if you find a t-score that puts you further to the left than negative 1.76, you would reject. Does that make sense? Okay. If you were to find a t-score from your data that is to the right of negative 1.76, we would fail to reject. Okay. So this t-score here will place you either on that side or on that side. Okay. And you decide to either reject or not reject. Is that okay with everybody? And that's using critical values. Okay. Now, let's put the t-score right here. Okay. So if the t-score was right there, would there be an area that is associated with that to the left? Does that make sense? Okay. Much like we know, if I were to go to Excel and type in t.dist, okay, now it's going to ask me for x. So I'm just going to type this number in right here. Okay. And we'll type in degrees of freedom, which we said was 14, and then we'll type in true, because that's just what we always have to type. That's a constant, because that means it's going to cumulatively add all the areas from negative infinity up to negative 1.76 underneath the curve. And what does it give me? It gives me 5%. It gives me that area that is all red here. Does that make sense? And that should make sense to us, because that basically undid what we accomplished when we found this to be the critical value. Does that make sense? Okay. So what I'm trying to say there is, if I were to, let's say that we run through our data, we run through this thing right here, and let's say we get a t-value from our data, and it's, let's just say, negative 2. Okay. So would you guys agree that that negative 2 as a t-value, if I'm using critical values, that negative 2 is to the left of this, right? Okay. So you would reject it, correct? Okay. But what we're going to do when we use p-values is that we know that this red area is 5%. This blue area is attached to this negative 2. And we don't know it yet. So that blue area, what I have to do, okay, so I'm looking at, and it should be a negative 2. So I'm looking for the probability, okay, that they're going to spit back, or the area that they spit back, that is from the left, from negative infinity up to negative 2, 14 degrees of freedom, cumulative, hit enter, and it gives you 0.03. So what that means to us is that this blue area, that's your p-value of 0.03. Does that make sense? Okay. Now, we were supposed to reject this off of critical values, right? We should still reject it no matter what tool we use to compare. You should still get a rejection. Okay? So how does that p-value relate to the alpha value when we reject? Because there should be a rejection. What is that blue area in comparison to the red area? Is it bigger or smaller? It's smaller. So when the p-value is smaller than alpha, that results in a rejection. Okay? Here we see 0.03 is less than 0.05. Does that kind of make sense? You're doing the exact same thing. Here, okay, if I found that to be a t from our data of negative 2, well, I compare the t from our data, the test statistic is what we call that, and we compare it to the critical value. And because it's further to the left, we reject. Okay? But if I'm using p-values, we compare the area of our t statistic, okay, in this case the left area, and we compare that to alpha out of the problem. Okay? But my hope is what we see here is that that p-value is attached to that. Much like this critical value is directly attached to alpha. Okay? So we can either find both t values, the critical value and the test statistic, and compare them. Or we can find the test statistic, find its p-value or its area, okay, and compare that to alpha. And when we use p-values, it actually allows you to do one less step because you only have to find the p-value because alpha is going to be given. Okay? If you want to use critical values, you have to convert alpha into that number there, and then you have to determine your test statistic right there. And that would be two calculations that you have to do. If you use p-values, all you got to do is figure that one. Does that kind of make sense? Okay. I'm a fan. I think, it just in my, like I can do both, but if I had a preference, I'm going to use critical values because it makes more sense to me visually. But my hope is that if we can make the connection that using critical values and using p-values is actually identical, then the hope is that we can use the one that's less work. Is that okay? All right, so we'll talk about it at the end of the period, but I want to give you an opportunity to go back and fix some of those things that we realized were maybe problems on the test or the quiz on Friday. Because it was all p-values, and if you were approaching that using the t-value approach or the critical value approach, I mean, you could have done everything right and had the right rejection, non-rejection results, but did everything intermediately wrong, and you could totally bomb that, right? Okay, so we'll address that at the end. We'll do this example with you. Actually, I want you guys to do quite a bit of this. Says a tobacco company claims that the best-selling cigarettes contain at most 40 milligrams of nicotine. Says this claim is tested at the 1% significance level by using the results of 15 randomly selected cigarettes. So the mean was 42.6 milligrams, and the standard deviation is 3.7 milligrams. Says evidence suggests that nicotine is normally distributed. Okay. All right. Says, is this a Z-test or a T-test? What are our thoughts on that? Z-test or T-test? What is the concept that allows me to distinguish T versus Z? Okay, so samples less than 30, that's one identifier. Now, we could still use a Z-test if the sample is less than 30, okay, as long as we are given the population standard deviation and we're told that the population is normally distributed. We are told that the population is normally distributed, okay? So we've got the idea that maybe because it's less than 30, we're kind of going to sway to the T-test, okay? But that's not the 100% identifier. That's not the most accurate identifier. Do we know the population standard deviation? No, we know the sample standard deviation, right? So those two things in tandem are important to have together to decide what test to use. And if you remember back to Chapter 8, we had this thing here, right? Okay, so the idea was, okay, is n greater or equal 30? So that was the question. We had a sample size, like it said 15. So we would have said no, okay? Was the population normally distributed? Yes, it was. It was told that, or we were told that. Now what we have to do is still, you see how we still have to make the argument on this, whether we know the population standard deviation or not. Because we could still use the Z-test. If all that stuff was true, we could still use the Z-test if we knew the population standard deviation. Okay, but in this case, we're going to go to the T-test. Okay, so that's step one: identifying what test you're going to use. Okay, what are the degrees of freedom in this particular problem? If that's my sample size, then degrees of freedom are one less, right? So degrees of freedom are 14. All right, let's determine the hypotheses. So we're going to go H sub 0 and H sub 1. Okay? So the tobacco company claims that its best-selling cigarettes contain at most 40 milligrams of nicotine. What does at most mean? Say again? That's the highest it can get. Okay? So for at most means you're not going to have one over 40. Okay? So how can I phrase that with an inequality if mu has to come first? Should be less than or equal to. Okay? If I wanted to go greater than, the word would have to be at least. Because if it's going to give me a bare minimum, that's my starting point, and then anything above that, so that would be greater than. Does that kind of make sense? So at most, when it says at most, so if I think about a number line, and I put 40 on that number line, okay, and I say you are allowed to go up to that number line and put a dot somewhere, but the restriction is that you can do that at most 40. Okay, I don't know if that's the best wording of that, but that means you could go up to 40. You could put it there. You could put it there. You could put it there. But if you're at most 40, then you're not allowed to put it there, right? So then when I highlight all the places that I could put it, that would be less than 40. Does that make sense? Okay. Okay. So if it says at most, okay, so usually when we think inequalities, okay, they say less than, greater than. They kind of say things like no more than, no less than, at most, at least. When they say at most, can you be 40? 40 is something you're allowed to be here. So does that involve equality? Okay, so this one, the null hypothesis here, the null hypothesis is that one. That's and that claim that they're arguing, so the company claims at most 40 milligrams. So this is the claim as well. So the alternative hypothesis must be what? If this is less than or equal to 40, the alternative hypothesis has to be greater than 40. Okay? I think these types of questions are problematic because they don't use the word is. Okay? So we have to know that when we talk about at most, that I always put myself on a number line. Can I stand on top of 40? And at that juncture, if I'm standing on top of 40, I would say that it is 40. I am equal to 40. So then equality has to go in the null hypothesis, right? Okay. Some of the other questions we've done will tell you essentially, I think very explicitly, what both hypotheses have to be. I think this one does not do that very well. Okay. But we can still decipher it and figure it out. All right, everybody, those are your two hypotheses. Okay. Now it says, is this a right tail test, left tail test, or two tail test? It is a right tail test. So that right there, okay, remember that. I just go off the directions, but if I put mu first, that thing's pointing to the right. Okay, so it's a right tail test. Okay. So let's determine the p-value. All right, so the p-value, we're going to need I just always like to have the curve to draw on. Well, maybe. Wow, that's dumb. All right. So we need, if I'm going to determine the p-value, okay, we're going to compare that to alpha. If you remember, I said alpha was 1%. Okay? So we probably find our p-value. The first thing that the p-value is based off of is finding your test statistic. Okay? So I'm going to take t and set that equal to x bar minus mu over s divided by root n. Okay? I want you guys to take a minute with that information and see what you come up with for t. Okay? Find your test statistic. All right, so when I plug that information in, okay, I get 42.6 minus 40 over 3.7 divided by root 15, right? Okay. Now, just go back. They give us all the process data here, but this would be something that would be relatively easy for any researcher to do, okay? Once you're able to get the nicotine out of the cigarettes and be able to quantify that, okay, you're going to have your 15 components from that sample. You'll have those 15 data values. You can find their average at 42.6, and you can run through the standard deviation formula and find that 3.7. Does that make sense? These are all easily obtainable values. Running that through the T statistic, then that formula, you get 2.72. You guys agree with that? Yeah. So now let's just take this perspective. If I was going to compare that to a critical value, do I have the critical values yet to compare that to? No. So that's more work, okay? We want to compare this to p-values. So I'm going to find 2.72. 2.72. So maybe 2.72 on my curve is there. Obviously, we know 0 is there, so we're to the right, okay? Now, we want this area. That area right there is the p-value, okay? And if I can find that area, then I can compare that area to 0.01, and we'll be able to make our decision, okay? If that area, okay, is greater than 0.01, okay, we will fail to reject, which would mean that the critical value in the t-value, the t-value would be left of the critical value, okay? If it is less than, that would mean that the t-value of 2.72 is to the right of the critical value that was attached to that. Okay, and we'll do the critical value approach as well when we're done. But we need the p-value right now so I can compare it to that alpha. Okay, so we're going to grab Excel. Okay, Excel, the command to find an area is t.dist. Okay, we have an x value. Okay, our x value is 2.72. We have a degree of freedom, so that's still 14 because the sample is 15, right? Hit enter, and it gives me that in return. Okay, now here's the issue. And this a very, very large number, because we're only working between 0 and 1. So in comparison to 0 and 1, that's a very, very large number, right? Okay, when you have that, chances are you need to think about what that result means to you, okay? Because that would be all the area from the left added up into that 2.72. Is that the area that we want? No, we want the other side of that, right? So what do I do with that number to get that value that I want? 1 minus that. So 1 minus A2, give me that number there, 0.008. So the p-value, which a lot of times is written this way, the probability that the t-value is greater than 2.72 is equal to 0.008. Okay? So what we're saying here is that there is a 0.8% chance that I could get a sample that is more extreme than the one that we currently have. Okay? Pretty low probability there. Okay? Now, there's other ways of doing it. I think Blaze, you asked this the other day. If we go t.dist, okay, instead of doing like 2.8 7, 2 here, typing 14 are degrees of freedom and true, okay? Because the t distribution is symmetric, we can actually make this a negative, okay? If I do a right-tailed test, and if I make my t statistic the opposite of what I found it to be, does that give me the same area that the complement procedure gave me? And that might just be a quicker thing to use when you're using Excel to find those values. And basically all it does is it says, okay, well, what if we go, it says it's symmetric, what if we find the area of negative 2.72, it should, to the left of that, should be the same as the area to the right of positive 2.72. Okay? So now, when we make our argument, we always put the p-value first, always put alpha second. Okay? Because that's how we've written our rule on whether we decide to reject or not reject. Okay? So our p-value, 0.008, and our alpha level, 0.01. Okay, which one of those is bigger? 1% is bigger, right? Okay, so if we remember what we wrote last week, actually it was in 9.3 that we wrote it. If your p, this is why I always like to write my p-value first. Okay, if p is less than alpha, you reject. If p is greater than alpha, you fail to reject. So right now, what did we have? We had p less than alpha. Okay, so you reject. Does that make sense? Okay. Now, just real quick before we get out of here, if we were working with critical values, okay, we found our test statistic to be t was 2.72. Okay. Now, to compare that to something, I need a critical value. Okay, and however you want to write, I like to write as t sub alpha, so I remember that it came from alpha. That's where I got this value. Or you want t sub c. The way we do that is, because it's a right-tailed test, I'm going to take right here, t distribution. Basically right now we don't know that number. Okay? We're trying to find that for 1%. So we actually have to use the inverse to do that. So I'm going to write, I'm going to write here, go equals t dot inv. Okay. Now it says probability. Well, the probability that we're looking for was 1%. And we'll talk about the number that comes back here. Because it's a right-tailed test, so we should actually type at 99% there. Does that make sense? Okay. But 99% and 1% should be the same critical values. One's going to be negative, one's going to be positive. Okay. And we want degrees of freedom of 14. And it gives me negative 2.62. Okay. So we're changing that to positive 2.62. Is that okay, everybody? So 2.62, negative 2.62 would have been there, and that would have showed me this 1% there. 2.62 is right there, and it showed me this positive 1%, or this right-tailed positive 1%. Is that okay, everybody? Where was our test value? Our test value is to the right of that. That would be 2.72 right there. Does that make sense? That 2.72 falls in the rejection region, right? Okay. The reason we rejected it was initially because, let's look at, so this area here, this yellow area, was the area from the critical value, or sorry, the area from alpha that produced that critical value. Okay. So that area was 1%. This area, that green area, is 0.008 or 0.8%. Okay? You see how that area is smaller? When the area is smaller, it essentially tells me that the critical value is to the left of the test statistic, or the test statistic is to the right of the critical value. So it falls in the rejection region. Right? Do we see the comparison of the two things? Okay, I'm seeing some heads bob up and down. That's good. But if we go through the work and we lay them side by side, and we want to do this, a lot of times, a lot of different scenarios, the p-value technique is more efficient for us. Okay. A lot of times, like I told you, the statistical packages that we create, Excel, those types of things, we can do. So I think we're going to do this later on. We should have some time towards the end of the year. There are some built-in tools in Excel. You have to load a package, which it's already in your Excel program. You just have to tell it to basically display it for us. It's called this data analysis. And when we click on that, it's going to open up a bunch of options for us. Now, it doesn't provide anything currently that we've been working on. Okay, we need to get into some more complex testing. But you'll see that the thing that returns, okay, in Excel, the values that it always returns are p-values. Basically, what we'll do is we'll create columns for our data. We'll type our data in. We'll click on one of those tests, highlight our data, hit enter, and it will come up with a chart of a bunch of information. And most important information that comes out of there is the p-value, and it'll tell us to whether reject or not reject. So that's all your programs are going to do that. Maybe tomorrow we'll see what I've never really messed around with GeoGebra in regards to the probability calculator here. Let's go t-test. So let me just show you kind of here what this does. So if I type in null hypothesis, we said it was 40, right? Alternative hypothesis, we wanted a right mean or a right test. The mean we found to be, the sample mean, was that 42.6? Type in 42.6. Standard deviation was at 3.7. N was 15. Okay. Hit enter. Okay. You see everything that's provided here? Gives me my critical value, but now it doesn't tell me, or I guess that's my test statistic, but it doesn't give me critical values because I never reported alpha here, right? Okay. But what does it give me? It gives me a p-value, right? Okay. And the benefit of that is because I never reported alpha, because that's the idea of what a statistician does. They don't report alpha a lot of times. And you get to choose as the observer alpha 1%, alpha 5%, alpha 10%, and compare that p-value then to those chosen alphas. Okay? So they're not trying to pigeonhole you into a level of significance. I'm going to open up that quiz from Friday. Okay? It'll be due tomorrow morning by the start of class. I'll give you your best score. Okay? So we'll do that. I'll open that up here in a few minutes.